Okay, let's look at two kind of classic amusement park rides and how circular motion is involved. So the first one we're going to do the old loop-de-loop on a roller coaster. So this is some Mass M roller coaster car, and it's going to come down this hill and then go around this loop-de-loop, and it's going to make it around the loop-de-loop. And what we're going to be interested in right now is the normal force at the top and the normal force at the bottom. Remember, the normal force is that perpendicular force, and in this case, you'd feel that force as the force that the seat applies to your body. And again, you would feel like it's your weight. Again, your weight's not going to change. Your weight's always going to equal mg, but it's the apparent weight that you feel, because normally, well, if you're just sitting there, your normal force is up and the weight is down, so you feel exactly your weight. But in an accelerated case, you might feel lighter and you might feel heavier, because what you're sensing is the normal force. You're sensing the roller coaster itself pushing on your body. Okay, and then we have the rotor. I think back in the day they used to have this at COSI. They used to have this at maybe fairs. This is this circular kind of ride that spins and spins and spins, and it spins fast enough, and then the floor drops out, and it spins fast enough that you actually just stick to the wall. And we want to look at both of these things. Okay, so let's look at the roller coaster, and we want to look at the difference between what's happening at the top of the spin and then at the very bottom when you come out of the loop-de-loops. You come down here and you go around and then you go to the top. And I want you to think of, if you've ridden a roller coaster like this, of the sensation of your body. How do you feel in terms of your weight at the top versus the bottom? And I hope that you kind of feel lighter and almost sometimes even weightless at the top, and you feel heavy at the bottom. And I want to show you the physics behind those things. Okay, so let's look at the top. When you're at the top of the loop, my argument is that we've experienced this and that we actually feel lighter. And I want to show you that the normal force is less than mg. Okay, so at the top, if you draw a free body diagram, you certainly have mg down, but then the normal force of the roller coaster is actually also down, right? You're upside down and the seat is pushing you that way. And those are the only two forces acting on you when you're at the very top. Now your velocity might be going this way, right, perpendicular, but that's not a force, that's just the direction of your motion. Those are the only two forces on the top. So at the top, if we look at the net force equals ma, and we could say n plus mg equals m, and then a is centripetal acceleration, so it's the equivalent to v squared over r. And we can solve for the normal force, and again, the normal force specifically at the top is m v squared over r minus mg. And again, it is typically that the normal force at the top is this, then minus mg, and so that whole thing actually might be less than your actual weight. Now, it would depend on your speed. I mean, if you zoomed around this thing super fast, then even at the top, this term could be like triple mg, and so the normal force could still be bigger than mg, but we are subtracting mg, right? Gravity is helping us move in a circle, okay? What if we're looking at then the bottom, right? When you're coming out of this loop, when you're pulling G's, as they say. Well, at the bottom, the normal force is up. Gravity, of course, is down. And in this case, the normal force at the bottom has to overcome gravity to cause you to move in a circle. Again, if you think about the top, what is the top doing? Well, when you're at the top and you're moving around in this circle, right? Gravity and the normal force are accelerating you inward, right? They're both the force pointing in that same direction, which is bending your velocity down and making you move in a circle. Well, when you're at the bottom of this thing, gravity actually wants to make you go this way, and the normal force has to counteract the gravity to actually bend you back and move you in a circle. So the normal force minus mg equals mv squared over r. And so then the normal force at the bottom of a vertical loop is going to be mv squared over r plus mg. Not only does the normal force have to cause centripetal acceleration, but it also has to overcome gravity to do it. And so hopefully you can see that it is how we feel. Again, typically at the top we feel lighter, and at the bottom we feel heavier than mg. Okay, so that's the analysis. And the roller coaster is the exact same problem as if I looked at, sometimes we'll take a string and a ball and they'll whip it around in a vertical circle. And it'll be the exact same thing. The string, the tension in the string at the top isn't very much because gravity's helping you. Well, when the ball's at the bottom, you have to hold on to the string a lot more because you have to overcome gravity to make it move in a circle. So again, I don't know what kind of devices you might have at home to kind of test this out, but if you have something that you can swing it around, and if you swing it around, you'll feel like you barely have to hold on to the string when it's at the top, and at the bottom you got to hang on much bigger, and it's this exact same theory. Again, whether this is a roller coaster, a ball on a string, a fighter jet going in a loop-de-loop, it's that same thing. At the top you kind of feel a little weightless at times, and at the bottom you're going to feel heavier. We could even find, again, this is something we do more in the energy unit, but we could find the minimum speed in order to get around. What would the minimum speed here? Well, if you want to make it around this thing, how fast do you have to be going? Well, we can't make the normal force negative, so if we want gravity to be the only force making us move into a circle, and we want to be the minimum, that means no normal force. That means the track isn't going to help us at all. We can actually find for that velocity. So if we set mg, straight up mg, equal to mv squared over r, we can actually find, multiply by r, we can find that the velocity equals the square root of gr. And this is going to come up a lot. This is the minimum velocity necessary for vertical motion in order to be actually go in a circle. Again, think about the minimum. The minimum happens when the normal force or the tension goes to zero, and gravity is the only force that's actually pulling you down and making you move into a circle. Again, if you make velocity bigger than that, well then the normal force will kick in and it will help gravity. But if you fall for the minimum, right, this is v min, and any less than that velocity and you actually won't even move in a circle. You'll whip this around and boom, it'll just fall. It won't actually keep going in a circle. Okay, so that's kind of the analysis of a vertical thing. And then the other kind of amusement park ride I want to look at is the roto. Again, this is going to spin fast and fast and fast, and we got to think about this. So let's draw a free body diagram here. So we have the normal force, right? The wall. The wall is what's actually making us move in a circle, right? We're moving in this kind of circular path. The force, the inward force, is what's making us move into a circle. And then vertically, we have mg. And then what makes it so we don't slide down the wall? Well, friction is going to oppose that. And so what we have here is we can have two different F equals ma. We have F equals ma for circular motion, the inward forces causing circular motion. And then we have the vertical forces that, as long as we're stuck there, we're going to have ay equals 0. So let's look at the inward forces first. The inward force, again, the only force acting there is the normal force, and that's equal to mv squared over r. And then we have this, well, the vertical forces, we have friction up, we have mg down, and you know what? We don't want to accelerate down, right? We want to spin fast enough so we stick to the wall, so there is no vertical acceleration, so we don't slide down. So we know that's equal. Okay, and then here's where it can get interesting. What is the force of friction? Well, the force of friction is mu times the normal force. And what's the normal force in this case? Well, that's right here. And so we take this equation and kind of combine, and we say then mu times the normal force, which we know is mv squared over r, minus mg has to equal 0. And again, if this minus this equals 0, that means those two things are equal. So mu mv squared over r has to equal mg. And we can show that it's independent of mass. And that's really important. That's like a duh, right? This ride would be a terrible ride if you had to be spinning at a different rate for different people, right? If I get on the ride and my 9-year-old son gets on the ride, well, they have to keep us both up. And it's nice that it's actually independent of mass. So if we wanted to find the velocity you have to be traveling at, Or maybe we wanted to look at the omega. Remember, V equals omega r. Maybe we want to look at how fast we need to spin rather than how fast we need to be moving. Then we can replace V by omega r squared over r equals g. And we can then solve for omega. So if we solve this for omega, right, omega is going to equal, this is going to be a g r over, and then we're going to get a mu r squared square root. So if we simplify that, that's going to be g over mu r, and that's going to be omega. Okay, that's how fast you need to spin based on the fact that we're on Earth, based on the radius of this thing, and based on the coefficient of friction between your body and the wall. Okay, so I kind of gave you an example of two different amusement rides. I talked you through a vertical loop, whether it's a roller coaster, an airplane, a ball on a string. We looked at the difference between the normal force at the top versus the bottom. The bottom's going to be bigger because it's fighting against gravity. The normal force is going to be reduced by mg, so it's going to be smaller. You can actually look for the minimum velocity at which you need to spin and still move into a circle by letting the normal force go to 0 and setting gravity all by itself equal to mv squared over r, and we get the velocity minimum as the square root of gr. And then I looked at the roto case. Okay?